work on some verification of user interfaces. And this is work we've been developing for some years now with Michael Harrison in the UK. And here I'm going to talk a bit about how we apply this work to a system on the aeronautical space that was done with population Miriam, Alves, and the models I'll talk about later were done by Sousa, which was the student here. So to start with, I'd just like to explain a bit where we come from to this work. So our starting point is that when you develop a dependable device and you plug it in front of the user, then you really don't have a guarantee that the working system, so you're saying that the system is the combination of the user and the device, will be dependable because of the impact users will have on how the device is operated. So impact of users on system disasters, anticipate, that will create problems for the dependability of the resulting combination of user code device. And this comes from the fact that a number of factors actually, but I have three main factors here in the slide. So users will behave unexpectedly, so it's hard to predict what they'll do. And the other day I was seeing this photo of a cockpit where someone had managed to fire a gun through the fuselage. The gun was there to improve safety, but in the end it created safety risks. Another problem is that not only users will behave in unexpected ways, but also they will change their behavior when they start using a specific device. So they will adapt to it. And for instance, can introduce safety features like features to prevent the landing gear of an airplane to retract too early during takeoff. After that was done, it was observed that pilots would start retracting the landing gear earlier than before because they knew the system was only do it at the appropriate time. But of course, that kind of breaks the safety argument because now the user is in fact always doing the wrong thing. And finally, users must understand the devices, so we have to design the devices in such a way that users will be able to use them. And if I'm not, when we're talking about interactive systems and dependable interactive systems, mission critical interactive systems, we have to consider the user doing the design of and the analysis mainly what we get to here of those devices. And that's what we've been working on. And we're still using formal verification techniques. So most techniques to analyze user interfaces from a human-computer interaction perspective are not very exhaustive and are not really repeatable, so they don't really provide any guarantee in what relates to safety. So the work we do is based on models. So a lot of work I've been hearing about is about analyzing code. Here we're dealing with the design time. So our approach is meant to be analyzing the design of the device, not the actual implementation. And so we're dealing with models of the user interface. So we start by creating a model of the interface in a domain-specific language. Can either be because we're designing some new device, or maybe we have a device and we want to analyze it. And not only do we develop this model and also the languages later, we also develop properties that the model should have. So these models are actually some sort of, can be translated into some sort of finite state machine, like we heard earlier today. And these properties are properties of the behavior of the finite state machine. And they will include things like safety properties that the user interface will not allow me to reach some unsafe state, or Learning properties like the interface will allow me to do something that I want to do in the interface. But also user-related properties or usability-related properties like checking that interface always provides feedback, and that interface always responds consistently to certain operations, certain interactions. And once we have the model and properties, we then run them through a verification tool, in this case a model checker, IV&V. I don't know so most of you are familiar with model checkers. The idea is that the tool will go through the finite state machine that represents the model and will explore all possible behaviors, trying to identify some behavior that falsifies the property. And when it identifies one of those behaviors, then it will present it to us, and that's what we call a potential problem. Potential in the sense that we have to analyze it to understand whether it's actually a problem or not. There's some reason why it actually might not be a problem, in fact, a real problem. Maybe because the model is an abstraction of the actual device, or maybe the abstraction process is responsible for that particular issue. Or maybe because if you are considering users, there's sometimes we might be, for instance, trying to prove that user interface always provides feedback, and we might identify some situation where feedback is not provided, but we might, by analyzing this specific situation, decide that it's not really a problem not to have feedback in that case, because maybe the user has enough information to use the system safely. So we have to do this analysis. We can create scenarios based on the behavior that the tool produces, the traces, and then we might redesign the system or rework the model. So to summarize, we have models that describe the system as designed, not in terms of implementation, although we could think about using models. We have also worked with models that can become into implementations and analyzing those. We have properties. I didn't say in the previous slide that writing the properties is actually quite hard sometimes. So we develop property patterns that help us both in terms of identifying useful properties, and then also in terms of writing the appropriate logic or expression that captures the property. And then we perform verification to identify interesting traces that show situations where the property fails, and then analyze those by the creative scenario. We can also use those traces to run prototypes, and eventually we will rework the design and improve it. Of course, we don't propose this as the only way to analyze a given design, so this slide tries to show a bit of how we see this fitting into the process of development. Here we have the prototypes and the model side by side, and there's arrows saying that we refine the model into a prototype and we can abstract the model from the prototype. Actually, at the moment we have made this connection a lot stronger, and we are running the prototype from the model, so that the model is actually run, and then we make the prototype, so they're converging into just one entity, the prototype and the model. And we can use the model to perform formal verification, so exhaustive analysis of behavior, and can use the prototype to do as a sort of analysis like a corrective session or walkthroughs, whatever. And so we, in a way, we're trying to complement the techniques with a more formal approach. To support this process, like I said, we developed a tool which is called the IV Workbench. This tool has a plugin architecture, so we can connect different plugins to it. At the moment, we have a number of plugins already developed. So we have a plugin to edit models, which is there on the top left. Also, a brief demo of the tool later. We have a plugin to write properties. We have a plugin to analyze the resulting behaviors, so the traces. we are also developing plugins to create prototypes or to animate models. And the idea of generating scenarios to illustrate is something that also interests us a lot, but at the moment we haven't done any real substantial work on that level. But you can see here at the bottom right, we are using IV&V as the verification engine. So our language is translated into IV&V, and it's IV&V that produces the traces that we then can analyze. We're also actually at the moment playing with PBS. So we already have a first version of a translation from our model to PBS, so that we can use to improve our performance analysis, because the model checker is good for some types of analysis, but improving it is good. It's better for another type of analysis. So we're trying to explore the interplay between model checking and improving, integrating them both into the platform. Here on the bottom left, we have this new surfer module. This is some work we've been doing in reverse engineering the code into models, but that's outside of the scope of this talk, so I won't talk much about that. So before I go into a demo, I just want to show a brief example of what the language looks like. So on the right here, we have an archive of the node control panel of MD88 aircraft. And here we have just a little bit of a model that was built to represent parts of this panel, just the bits that are in Latin way. So the language has a kind of an object-oriented flavor. Instead of objects, we have interactors, and the models are composed by aggregating interactors inside other interactors. So kind of like reminiscent of how you build the user interface that you compose components one inside of bigger components. So in this case, we're saying that the MCP interactor aggregates 3 dials, where each dial represents the nodes here and the associated values, so one for velocity, one for time rate, one for altitude. And then we use attributes of the object or the interactor to present information that is visible on the display. In this case, we have the pitch mode and the state of the output capture, represented here to attributes, pitch mode and out. And actions so commands that the user can issue, so in this case, these buttons here are represented by actions. Now notice that these annotation here on attributes and actions, this means that these are visible, so they're made available to the user. There's an action here, enter18, which is an internal action that the user cannot execute it, so it's an automatic thing inside the logic of the node control panel. And then we have to express behavior. So the way we express behavior is to say how the actions change the attributes in the display. Of course, we will most of the time use internal attributes to express the logic and to make it behave. So to give it more information, most of the time just what's in the screen is not enough. But basically, these actions will change, say how actions change attributes. So for instance, here I say that if I press enter IAS, then the pitch mode becomes IAS, and the alt is unchanged. So the priming is the value of the attribute before the action, so after the action, sorry, and without the priming before the action. So, and besides these rules that we can write saying how the actions change attributes, we can write other rules or other actions, if you will, saying when an action is permitted and where an action is possible, or when an action is mandatory. So with that, besides that, it's basically just positional logic, and we can then express the behavior of the device. So this is done from an external perspective. Of course, we have also to say something about internal most of the time. So in this case of the node control panel, we have to model the altitude of the plane and how the pitch mode is altitude and things like that. but only as far as it's needed to model the right behavior of the interface. So this is a small demo, the proof. Okay, so we have this editor, so this is the model editor. It has a graphical mode where we have a notation that is quite similar to YAML class diagram. We're loading the project now. And we have a text notation which we use most of the time. So this model here is actually not the remote control panel, is a model of a medical device, infusion pump. And for our standards already quite a big model, so it's over 1,600 lines of code or model. But this is a quite detailed model of an infusion pump, which Michael has developed. So it's been doing a lot of this lately. Once you write your model, then you can go into the properties editor. Here on the top left, you have the pattern library. If you open these folders and you have the patterns, you select one pattern, and here on the right, you can instantiate the pattern by filling in the blanks on the property generated. In this case, just make things quicker. I'm just going to show how to choose the property here. Then we use the verification button, the inside button, and the model that we have written before, we have seen before, gets translated into IV&V, and then IV&V performs the verification. In this case, after 12 minutes, we get the result, and it says that the properties we're trying to prove is false. And then we can go into the trace analyzer to see the trace that was produced. There's a number of different representations. So there's the tabular representation where columns represent states and lines represent attributes or actions. And there's also a state-based representation where you can see how state change the result of action factors. That's basically the most important bit of the tool. There's other things like the possibility of highlighting states based on conditions and things like that to help analyze the traces, and there's the animator. But I think that gives you an idea of what the tool is about. So when we had this tool, we keep developing it, and then when I met with Miriam, we were interested in trying to apply this to bigger systems. We had analyzed, at the time we had analyzed a couple of real devices. Since then we started to work on the medical devices, but we still are interested in trying to apply this to bigger systems and actual systems to see how far we can go with it. And so the idea came out of trying to analyze the part of the separation and testing one system from this particular aeronautic space in Brazil. So there's a picture here of the system, composed of 6 subsystems, and of these we built models for the flight event systems network system, which is this EV system, and for the electrical network system. All of the systems have a user interface, a screen. This screen has a number of a display, sorry, and this display has a number of screens and can navigate between screens. The screens show you information about the status of different processes and different pieces. If you know more about this kind of system than I know, sure. So what we modeled was just the user interface, not the rest of the more hardware part of the system. So I'll just talk a bit about the user system. So the first thing, the first challenge we had, and it actually turned out to be an interesting one, was that we didn't really have access to the system. So in previous situations and also in other situations we have had since then, we usually have access either to some kind of technical information about the system implementation or access to the working system, and we can try it out and we can try to model or create a model as fast as possible. In this case, we didn't really have that, so we only had the operations manual to work with, which was interesting because what ended up with was not a model that reflected the design of the system that we are used to, but actually the model reflects the knowledge that is provided to the operator through the manual. So in this way, when we are putting properties, we were actually putting properties about the information that was provided to the operator more than the actual system design. And because we wanted to test how far we could go with the language and tool and the model checking, we know that one of the problems with model checkers is take explosion. So if the models can become very big, and then you need lots of time and lots of memory to perform the verification. So because we wanted to see how far we could go, we didn't care, we didn't try to make the model very small. We decided to go for a 3-layered model where we had interactors to represent variables, and each kind of screen, we modeled 4 screens for this system. Each kind of screen has a different variable because they have slightly different behavior. So each variable has a value, has an attribute saying if it's a critical variable or not, has some range setting what the normal operating units are. So we created an interactor for each of those, and then we created a model for each of the panels, each of the screens, which aggregates a number of variables and also has attributes depending on the type of the panel. There's 2 particular panels here, the large panel and the left panel, because what happens in these, the schematic panel and the telemetry panel, is that variables that are outside of the normal operating range, you can generate alarms or alerts, right? And then they are represented with different colors. And so these alarm and alert panels, they can show an overview of what is happening in all the other panels. And so we created this model for these panels, and then the main interactor here navigates everything and coordinates what is happening. So because this is an hierarchical structure, we have to perform coordination at top level. So this main will say what happens in the large panel when some variable in the schematic panel becomes an alert, for instance. So building the models from the manual was a key process, so to speak. First, we had to identify variables and we had to identify actions for each of the interactors. That was relatively easy because we had screenshots and we could look at the screens and say, okay, that's information that's available, that these are the actions. We could quickly define that. Then finding the behavior of the model was a bit more work, so we had to go through the text and interpret what was being said. And I have here a small example. So this is a bit of a manual which explains when the variable becomes yellow and starts blinking. And so this is a translation from the original, which was in Portuguese. And what we said is the variable will become blinking yellow when if it's a critical variable, when the current value is within the alert range and it's not acknowledged, and it's not within the alarm range of an alarm that's trusted. And we can write that in our logic. So we have an attribute to say that the variable is critical or not. And so we can blinking yellow when it's critical, and the value that we're trying to set, which is this _v, it's in the right range, and the alarm state has no alarm set. So that this corresponds to that text over there. And we can do the same thing for the case where the variable is non-critical. When it's non-critical, then the value is within the range for alarm. And so this is a simple expression. So it's non-critical, the exclamation mark is the not, and the value is within the right range. And then we can write an action. And to expect you to read it, but basically it says that if I set the value of a variable to the store V, then if the conditions for looking yellow that are highlighted there hold, then the value of the variable will become the underscore V, and the color will become yellow, and the characteristic will become blink, and the other bit confused. That can be used for other parts of the menu. This doesn't capture the bit here in white about when it becomes fixed red, because if this is a different color, we have to write another action for this bit. But it's just easy out. Running out of time to also fix it. It's easy, similar. So we played around with different configurations of the model, trying to introducing different numbers of variables in the panel, trying to be more complete or less complete. In the end, we concluded that because of the coordination between all the variables, especially the alerts and alarms panel, need to coordinate with all the other panels to show the right alarms and alerts. If we started including too many variables, then the model would start taking a long time to verify. And also, we also noticed that because the variables were all behaving the same, actually by introducing more variables, we weren't really gaining anything. Because having 2 or having 5, it was, in terms of the behavior of the overall behavior of the system, it was basically the same thing. So these numbers are for a case where we had 2 variables per panel in the telemetry in the synoptics panel, and that's a small model which captures the logic that is put forward in the manual. So it didn't need a lot of modeling to model that. So moving on, after we had the model, we could then start thinking about analyzing it. And even before starting to try to verify requirements, we do a first check about the sanity of the model. So just to check that we didn't make any mistakes, we had to put some obvious properties to see if everything is working as expected. We can also simulate the model now. At the time, we didn't have the simulators. And actually doing that, we found was when we found one issue. So we were trying to prove a very simple thing, that the variable could be in the line. So basically saying actually that color could become red, which is a manifestation of being in the line. So this property just says that if a variable is the color green, that it can become red. Actually, it says the opposite. It says that if it has the green, it will not become red. This is because if you try to prove that a green variable can become red, the model checker says that's true, and you know that this is true, but you don't need to learn a lot more. So usually we find it more interesting to try to prove the negative to see which trait comes up. So here we're trying to prove that if the variable was green, it wouldn't be possible for it to become red. And of course this is false, because if the alarm is generated, the variable will become red. But the interesting thing was that the trait that was generated wasn't really what we were expecting. This is a very small trait because basically it's green and then becomes red, but it shows a situation that actually shouldn't occur. So it shows that the variable is green, it's not in an alarm or alert, and then if value is set to 5, it generates an alert, but the alert becomes acknowledged automatically, and that shouldn't happen. And so the variable becomes red, but a fixed red should be blinking and shouldn't be acknowledged, because for a variable to be an alert to be acknowledged, that's the operator has to do it. And so at first we thought that we had something wrong with the model. We went back to the model and realized that there was no information about what happens when an alert happens in a non-critical variable, which is the case here. Then we thought we probably have forgotten something. We went back to the manual and we realized that actually the manual also doesn't say anything about that. So there's no information on the manual about non-critical non-critical variable becoming having an alert state. We could assume that it's not possible, but that's also not the case there. And actually, we couldn't really, talking to people in the institute, we couldn't really come to a conclusion about that particular issue. So I'm really running out of time, so just to conclude, what we learned from this is what's possible to write a model independently from the actual system, just from the documentation, and we could actually provide some interesting or not with some interesting insights about the system from that model without having access directly to the system. We still think we believe that doing this kind of analysis is relevant for critical systems, or in this case for the interface of critical systems, because it provides us with a level of parametric analysis that other techniques, especially from the interactive area, don't provide. Because I think I've run out of time, I'll stop here.
Yeah, all right, thank you, Jose. We'll entertain questions for Jose over in the breakout session, and we're going to move right on into the next presentation.
Okay,